Now we're going to look at the sum of an infinite series. The word infinite means not finite. In other words, I'm not going to stop adding at the 7th term or the 100th term or even the millionth term. We are actually going to sum up all of the terms that go on forever. So we're going to sum up the infinite number of terms, so it continues forever. Is it possible to add up an infinite number of values? And in this case, the answer is yes, but only under certain conditions. So number one, it has to be a geometric sequence. So number one, you have to be able to find an R value. The second condition is that only if the sequence converges. And that means that the R value, the absolute value of R, has to be less than 1. So these are the conditions that must be met. Alright, so we say that a sequence converges if the R value, or the absolute value of R, is less than 1. So let's look at these two sequences. We have, for the first one, we have 18, 6, 2, 2/3, 2/9. Now we can tell here that the numbers are getting smaller. But let's do two things to see if a sequence converges. Number one, is it a geometric sequence? Okay, let's see. We need to determine an R value. So what do I multiply to get from term to term? And remember, sometimes it may not be easy to tell, but we can always take two terms that are side by side and take the later divided by the previous. So if I do 6 divided by 18, I get 1/3. Okay, let's verify again. That would be 2 divided by 6, which also gives me 1/3. And let's just take these two. Remember, any two terms in the sequence, side by side, if I take a later divided by a previous, then I should get the same number. So if I do that, I have to flip that bottom fraction and multiply. The 2's cancel. 1 and 3, so 3 goes into 3 once, 3 goes into 9 3 times, so I get 1/3. Okay, so I have convinced myself here that I do have a geometric sequence and the R value is 1/3. Does the sequence converge? Well, the condition for converging means that the R value, or the absolute value of R, is less than 1. So if I take the absolute value of a positive 1/3, I get 1/3, and 1/3 is definitely less than 1. So we say the sequence converges. So let's take a closer look at the terms of this sequence. We have 18, 6, 2, 2/3, 2/9. Now those are the exact values, but let's start thinking about the approximations of those. That would be about 0.66. 2/9. If I put that into my calculator, I get a decimal approximation of about 0.22. We notice that the terms of the sequence are getting smaller. And that's what's going to happen when your sequence converges. The terms of the sequence start to get smaller and smaller. Now, the R value we said was 1/3, so let's find a few more terms. If I multiply 2/9 by 1/3, I get 2/27. And then multiplying by 1/3 again, I get 2/81. And then multiplying by 1/3 again, I get 2/243. And then multiplying by 1/3 again, I get 2/729. And then I get 2/2187. We'll stop there. But let's look at the decimal approximations of each of these. 2/27 is pretty small. I get about 0.07. 2/81, I get about 0.02. 243, I get about 0.008. So now we're getting really small. And then going again, I get 0.002. and then one more. I get 0.0009. So we start to see that the terms are getting smaller and smaller. Now let's look to see what would happen if I started to sum these terms together. The first 5 terms look like they're going to give us the bulk of the sum. When I add all of those terms up together, I get 26.88. Now let's see what happens when we sum the next 5 terms. So let's take these 5 terms, I'm going to put them in my calculator, I'm going to add all those decimal approximations together, and all together I get about 0.1. So the first 5 terms gave us a total of 26.88, but the next 5 terms in the sequence only give me about 0.1. So what happens as we move further and further down the line, the later terms are going to become less significant and contribute less to the overall total. So since the sequence is geometric and the sequence converges, then we know that we can actually find a sum. So how do we find the sum of an infinite sequence or an infinite series? We're going to have this formula here that we can use only if the R value is less than 1. So only if the sequence converges. So let's find the sum here. Now I can make a guess. I have 26.88 plus about 0.1. I'm going to guess about 27. Alright, so let's use our formula. So we're going to have the sum. We'll have our little infinity symbol for the infinite number of terms. So it's going to be the first term of the sequence, which in this case is 18, divided by 1 minus the R value, which we said was 1/3. Alright, I'm just going to do this calculation here by hand. So that would be 18 over. I need a common denominator of 3 to combine those fractions at the bottom. So that's 3 over 3 minus 1/3. So that's 18 over 2/3. And I'm going to flip the bottom fraction and change to multiplication. So that would be overall 2 goes into 18 9 times, so that's a total of 27. So the sum of the infinite number of terms in this sequence totals up to be 27. So that makes sense. The bulk of the sum seems to come from the first 5 terms there, and then the rest of them are just not going to add that much. Alright, so our final answer there would be 27. Alright, so let's look at our next sequence. We have up here that the series or the sequence diverges if r is greater than 1. So here we have 2, and then we have 6, and then we have 18. It looks like I'm multiplying by 3 each time. So I would say we have a geometric sequence with an r value of 3. So our first condition is met. It is a geometric sequence. However, the second condition fails because in order for the sequence to be added, in order for the sequence converge, my r value has to be less than 1, but in this case the r value is greater than 1. So in this case we would say the sequence diverges. If the sequence diverges, then a sum is not possible. So what happens in this case is we start to look at the terms. The terms are getting larger and larger and larger. The next term here would be 54, and then the next one would be 162. If I start to try to add those numbers together, the first 4 terms would give me 80, and then you notice that I'm contributing more as I go forward, so the next term would give me 162. And so because the terms are getting larger and larger, the remaining terms added in actually contributes more significance. So the terms actually become more significant. So the sum is actually going to just grow infinitely large. Infinity is not a sum. So the overall sum, finding that specific total is not possible. So when you're working with an infinite geometric sequence, with your r value being greater than 1, the sequence diverges. Therefore, the sum is not possible to find. Now that also implies that you can't use the formula. Now if you try to use the formula, what happens? So let's try. We have 2, that's the first term of the sequence, divided by 1 minus the r value, which in this case is 3. So if I use that formula, I get something that doesn't make any sense. That's 2 divided by, what is that, -2? We get that the sum of these infinite number of terms is -1, and that clearly contradicts what we've already seen just by adding the first 5 terms of the sequence. So this does not make any sense. So if you say that the sum is not possible, that the sequence diverges, you cannot use the formula. Telling me that the sum is not possible and telling me the sum doesn't make any sense. That would be contradictory information. So if you decide that the sequence diverges and the sum is not possible, then you cannot use the formula, and you should not use the formula to try to find the sum. So example 3 says to find the sum if possible. And when we look at the sigma notation, we notice it says to sum from k equals 1 to infinity. So we are asked to sum an infinite number of terms. If you are asked to sum an infinite number of terms, you want to first ask yourself, is it possible? In order for it to be possible, it has to meet 2 conditions. It has to be geometric, so you should be able to find an r value, and 2, the sequence has to converge, which means the r value has to be less than 1. So let's see if our sequence meets these 2 conditions before we try to find the sum of these infinite number of terms. All right, so let's find the first term. Plug in k equals 1. And the second term, we're going to plug in k equals 2. And then for the third term, I'm going to plug in a k value of 3. And then for the fourth term, we'll plug in a k value of 4. Alright, now we could go on for all eternity, but of course we won't, and we really can't. So I'm just going to put ... to say that the sequence continues on. Alright, so let's find that first term. Our first term would be multiplying those 2 fractions together, because 3/4 to the power of 1 is 3/4, and then we can do our multiplication. Let's not simplify here, let's just do the multiplication. We'll simplify later if we need to. So top times the top would give me 6, bottom times the bottom gives me 4. Okay, for the second term, we have to square first. Squaring the top, I get 9. Squaring the bottom, I get 16. If I want, I can go ahead and simplify that. I get, what's that, 3/2. And then simplifying here, we have a common factor, what is that, of 2. So divide by 2, I get 9/8. Okay, we'll keep going here. The next one is 2 times 3/4 to the power of 3. So we're going to cube the top, cube the bottom. We'll simplify here by canceling common factors. 2 goes into 64. What is that? 32 times. So I get 27/32. Okay, and then the fourth term, we're going to raise each one of those to the power of 4. What does it give me? 3 to the power of 4 is 81. 4 to the power of 4 gives me 256. Canceling common factors. 2 goes into 256 128 times. So it gives me 81/128. Alright, so let's see if we can figure out what the r value is. Is it a geometric sequence? If it is, then we need to be able to figure out the r value. So to get from here to here, I would need to multiply by, looks like multiplying the top by 3 and the bottom by 4. Looks like the same thing here. To get from 9 to 27, I'd have to multiply the top by 3. I'd have to multiply, looks like 8 times 4 to get to 32. So it looks like the consistent r value would be 3/4. So we've confirmed that it's a geometric sequence and the r value is 3/4. Does the sequence converge? And it does converge because our R value, 3/4, is definitely less than 1. So we have a geometric sequence and it converges. What that tells us then is that we can use now the formula for the sum of an infinite series of a geometric sequence. So the sum of an infinite number of terms is going to be the first term of the sequence, 3/2, divided by 1 minus our R value, which is 3/4. Okay, you're welcome to put that into your calculator to find that exact sum, or you can do that by hand. So let's just do that by hand. I need a common denominator in the bottom. That would be 4. So that's 4/4 minus 3/4. So in the bottom I get, was that 1/4? Okay, we have a fraction divided by a fraction, so I'm going to flip the bottom fraction and change to multiplication. So you get 12/2. When I multiply across, 12 divided by 2 simplifies to give me a final answer of 6. So the sum of these infinite number of terms of this particular sequence will be a total of 6. In example 4, we're asked to find the sum if possible. So when we look at our sigma notation, we're asked to find the sum of the terms from k = 1 to infinity. Since we are summing an infinite number of terms, we need to ask ourselves, is this sum possible? To be possible, first of all, we want to verify, is it a geometric sequence? And then secondly, does the sequence converge? To determine if the sequence is geometric, we need to find an R value. So let's find the terms of the sequence. We'll first set k = 1. And then we'll set k = 2. We'll set k = 3. Alright, I'll stop there for the moment. We know that we could continue on to find an infinite number of terms of the sequence by changing the k values, but let's just stop there, see what we find. I have to do the exponents first, so 1 minus 1 is going to give me 0. Anything raised to the 0 power is a positive 1. So we have 3 times 1, which gives us a first term of 3. Alright, the next one is 2 minus 1. 2 minus 1 is 1. 3/2 to the power of 1 is 3/2. Alright, so let's simplify. I'm just going to multiply across. 3 times 3 is 9. 1 times 2 is 2. Alright, the third term. 3 minus 1 is 2. So I'm going to square the top, get 9. We square the bottom, we get 4. Think about that as a fraction and multiply across, we get 27/4. So what is the R value? Let's see. Let's think about this as 3/1. What do I need to multiply times this fraction to get to this one? It looks like 3/2. So multiply the top by 3, multiply the bottom by 2. Okay, to get from this term to this term, looks like I multiply the top of the fraction by 3 and the bottom of the fraction by 2. So it looks like that would be our R value. So we do have a geometric sequence and the R value is 3/2. Sometimes we have a hard time with fractions deciding is that greater than 1 or less than 1. So let's put that into our calculator, and that tells me that the decimal value would be 1.5. So does the sequence converge? The answer is no. The R value, 1.5 or 3/2, is definitely larger than 1. So this means that for this example, the sum is not possible. Before we go on to the next example, I want to make a little note. When do we ask ourselves if the sum is possible or not possible? We only do that if we see the infinity symbol. So if we're adding up or summing an infinite number of terms. What if I have this exact same question, almost exactly the same, except at the top, let's say I have 150. So let's say everything else is the same. In other words, it's geometric, because the r value would still be 3 over 2. But do I need to ask myself, does this sequence converge? And the answer is no. The only time I go through does the sequence converge and to determine if the sum is possible or not possible is if at the top I see an infinity symbol. If I do not see an infinity symbol and I actually see a finite number, that's a finite sum. Finite sums are always possible. So be careful. Don't say something is not possible just because the r value is greater than 1. That situation only applies if you are adding up an infinite number of terms. If you're adding up a finite number of terms, the sum is always possible. You can definitely take 150 numbers and add them up together. That is not a problem. Now, if you do have a finite sum, we want to remember that the formula for a finite sum is going to be different. So it's going to be following that formula that we talked about in the last video. Alright, but a finite sum is always possible. The only time that you would be able to say not possible is if you were summing an infinite number of terms. Here we're going to look at a word problem that deals with geometric sequences and the infinite number of terms of a geometric sequence. Alright, so here we have that a ball is dropped from a height of 1,200 feet. Each time it strikes the ground, it bounces up 0.4 of the previous height. What height will the ball bounce to? After it strikes the ground for the 4th time, what total vertical distance does the ball travel before it stops bouncing? Alright, so I'm going to draw a little picture to help us out here. To help us visualize what's going on, let's start by drawing a picture. So here we have a ball. And this ball is going to be dropped for the first time a distance of 1,200 feet. It's going to hit the ground and then it's going to bounce back up. Now, it says that after it strikes the ground, it's only going to bounce up to 0.4 of the previous height. So it's not going to bounce up as high, and in fact, it's going to bounce up less than half. Okay, I'm not going to so much worry about the scale here, but it bounces up to 0.4 of the previous height. So how high will it bounce back up? Well, bouncing back up 0.4 of the previous height, the word of usually means multiplication. So we're going to do 1,200 times 0.4. And that's going to tell us how high it's going to bounce back up. So it's going to bounce up 480 feet. Now what goes up must come down, so it's also going to go back down and hit the ground 480 feet. So the distance that it traveled up is the same distance that it has to travel back down to get to the ground. All right, so here's the first strike. Here's the second strike. Now we want to figure out what happens after that. Well, it's going to hit the ground, it's going to bounce back up 0.4 again of the previous height. So I'm going to take the last distance, and again I'm going to multiply by 0.4 to get the new distance. So that's 192. And once again, I'm not going to worry too much about scaling. There's our ball. So it bounces back up 192 feet. Of course, if it goes up that much, then it has to come down that much again to get to the ground. So it goes down 192 feet. Okay, so that's the third strike. Okay, we want to go again. Okay, so we're going to take 192 and the ball's going to bounce up 0.4 of that previous height. So I get 76.8 feet. Right, again, the ball has to come back down to hit the ground. It has to travel the same distance that it went up. So it strikes the ground again here for the 4th time. Now, part A says, what height will the ball be after it bounces, or after it strikes the ground for the 4th time? So how high will it go after that? So again, I'm going to take that 76.8 and we're going to multiply by 0.4, and I get 30.72. And then of course we know the ball is going to have to come back down to strike the ground again. So for part A, after that fourth strike, the ball bounces up to a height of 30.72 feet. Okay, so part B. Now part B is where things start to get a little bit more interesting. For part B, we want to know what is the total vertical distance. So when we mean vertical distance, we mean the distance that the ball has traveled, both going up and down. So we want to take all of these distances and we want to add them all up together. Now how many terms are we adding in together? Well, we're going to actually let the ball bounce out to infinity. So it's going to bounce as far as it needs to bounce until it stops. Now theoretically the ball does not stop bouncing, so we're going to let these number of terms go out to infinity. If we're going to let the number of terms go out to infinity, then we need to know two things. If I'm going to sum up all of these terms, that's the sum of an infinite number of terms of a sequence. First of all, I have to verify that I have a geometric sequence. And secondly, I have to verify that the sequence converges before I can do any summing. Now let's look at the distances that we need to add together. 1200 plus 4800 plus another 4800 plus 192 plus another 192, and so on. And then on to infinity. Now the problem that we have is this is not a geometric sequence. To get from here to here, yes, I multiply by 0.4, but to get from here to here, I don't multiply by anything. What you can think about it as multiplying by 1. To get from here to here, yes, I multiply by 0.4, but to get from 192 back to 192, multiply by 1. So all of the numbers I want to sum together actually do not form a geometric sequence. And if they don't form a geometric sequence, then I'm not allowed to use my formulas for geometric sequence. Alright, so here's what we're going to have to do. We're going to have to separate this into two sequences. We're going to separate it into two sequences based on the ups and the downs. So first let's focus on the downs. So we're going to separate the downward vertical distances from the upward vertical distances. So let's focus on the downs first. The downs would be 1200, and then 4800, and then 192, and then 76.8, and then 30.72, and so on. If I only focus on the down for each one of these, then I actually do have a geometric sequence, because that's 0.4, and then 0.4, then my R value is consistent to get from term to term. So we can actually use our infinite sum formula for that sequence. The sequence is geometric, and it also converges because our R value is 0.4, which is less than 1. So we're allowed to use that formula. So this is for the downs. So the first term of the downward vertical movements is 1200, and then I'm going to divide that by 1 minus the R value, which is 0.4. Okay, you can put that into your calculator if you want to, or you can do it by hand. Either way, we're going to get 2000. Now we want to keep in mind that that number only applies to the downward vertical movements, not to the total of all vertical movements. We need to add in the ups. The ups start at 4800, then go 192, and so on. Now the ups by themselves actually do, once again, form a geometric sequence. So if this is the first term of the upward movements, 48 to get to 192, that R value would be 0.4. To get from 192 to 76.8, that would be 0.4. So the ups and the downs separately are geometric sequences that converge. Now the upward movements start with a first term of 4800. Still has the same R value. So 1 minus 0.4, it's going to give me 480 divided by 0.6 again. And that gives me a total of 800. So in order to answer this question, we need to let the ball bounce out to infinity, and then we need to separate the upward and downward vertical movements into two different geometric sequences. Once I have all the ups and downs separated into two different geometric sequences, then I can actually take those two totals and add them together. So the total of all vertical movements then would be 2,000 plus 800. It would be a total of 2,800 feet for the total of all of those vertical movements, all the way out to infinity.